My name is Gerrit Nitters. I'm the distinguished lecturer for the valve stimulation, and the title of my lecture is Valve Stimulation, a New Challenge. I'm working with Shell out of Holland, and I'm very happy to be here. Before we actually start on the lecture itself, let's first define what we think is valve stimulation. There's a lot of different definitions. The definition I want to use is that it is any activity that increases the valve productivity by affecting the near wellbore area. So it means it's all about matrix treatments, which are restoring the natural productivity of a well, removing any sort of damage that may be around. We're talking about hydraulic fracturing, which is actually increasing the almost like the natural productivity of a well. Some people think that perforation, for instance, is a stimulation method under this definition because you do something to the near wellbore area, and by that means get better production. Very often without perforation you don't have any production whatsoever, and there may be even more. But I want to make sure that we're not talking about something that stimulates the entire reservoir. So it's not things like steam drive, water flooding, and it's also not on the other side. We're not talking about removing wax from a tubular. It's not to do with that. It's just the tiny little area around the wellbore. If we look back in history, the first acidizing treatment, which is supposed to be the first stimulation treatment at all, was done in 1895 in a well in, I guess, in Ohio Oil Company, so it should probably be in Ohio. And it was a very successful job initially. However, there was one slight little thing they overlooked, that steel also dissolves in hydrochloric acid. And by that, for that reason, after a couple of months, they had to shut in the well because there was no tubular left. And over the last little more than 100 years, this whole technology evolved to a very sophisticated type of treatment with computerized design and execution. We don't have a picture of the very first treatment, but this is a picture of the earliest acid treatment we can have photographic proof of, so to speak. It was a treatment done somewhere in the US. I haven't got a clue where it was. You can see that the use of safety clothing, etc., wasn't really on that. The guy just probably put on his head, not particularly a hard head, for the picture, I guess. And nobody would, while pumping, hold his hand on the Christmas tree these days, I would imagine. Likewise, we move to the next kind of stimulation treatment, hydraulic fracturing. It's a more complicated type of treatment. The first frac job done was in the Yucatan field in Kansas, 1947. I'm very glad I wasn't on location at that time. Again, safety was a little bit different. They used most likely gelled kerosene, which otherwise is also sometimes known as napalm. They probably must have had it from the Second World War or so left over. Pumping that stuff at high pressures is not a particular fun thing to do. It involved quite a lot of pumping and quite a lot of equipment already at that time. But in the 50s, 60s, we have a very rapidly increasing complexity of the treatment. The first treatment was done with crushed walnut hulls as proppant. Proppant is the material that you use to keep the fracture open. It evolved to sand, and nowadays it probably go even a little bit further than sand. I come to that. In the 60s, early 60s, I think the use of acid in combination with hydraulic fracturing was introduced, called acid fracturing, or fracture acidizing. There's different names for that. And the fluids we used to create the fracture changed from oil-based fluids to water-based fluids. Nowadays, probably about 90-95% of all the treatments are done with the water-based fluids. Highly sophisticated chemical compositions, a far cry from the first treatment with gelled oil. At the same time, there's a whole lot better understanding of the mechanism of hydraulic fracturing. There are very sophisticated models around. Just to show you a picture, again, this is the first hydraulic fracturing treatment. It's a very simple setup right here. There's some pumping equipment hidden here as well, and it all goes back to the well. There's probably some silos for fluids and stuff like that. I'm not really sure what each of these things is, but you can see it's a relatively simple setup. Fracturing fluids, they have that's the backbone of a successful treatment. If you choose the wrong fracturing fluid, you have basically you have a failure. You can actually, if you do it really wrong, you can lose the well. There's stories around of that quite dramatic. One well in Holland where they forgot, so to speak, to test the compatibility of the frac fluid with the mud that was used, resulted in a tremendous stiff emulsion, and the well didn't produce anything at all. We tried to remove it, unsuccessful, and the well was sidetracked. It can be very costly if we make mistakes over there. Different fluid systems for different formations, and you have to look at all the chemicals. Most of the chemicals are actually nowadays are liquids. There's a few exceptions, but most of them are liquid. And there's a whole range of fluids available. All the surface companies have their own tricks and have their own special frac fluids these days. Likewise, proppants. Early days, we had walnut hulls. Those were pretty popular materials anyway in the oil industry up to almost the early 60s even. Often also used as fluid loss materials and other stuff. For fracking, it soon was clear that walnut hulls are not really strong enough. If you have a fracture that closes on you, it's high pressures, and the high pressure causes the walnut hulls to crush completely, and you lose the fracture conductivity. So pretty soon after that, people went to sand. Most popular sand was Ottawa sand. I guess it's from Ottawa. I guess it's a mountain somewhere which no longer exists because it's all gone. Early 70s, people started talking about man-made proppants, bauxites, ceramics, and nowadays these are combined with resins to create resin-coated proppants. Resin-coated proppants are used to prevent proppant flowback. If you have, especially in gas wells, if you high rate gas flow, you can imagine that the proppant is dragged along with the gas flow. That is pretty much, that problem has been pretty much solved by the industry using resin coats. There are some issues. Sometimes you can't use a certain fluid with a certain resin-coated proppant again. So again, there you have to look at the compatibility, and you have to make sure that you have the right combination. Otherwise, you're in for disaster again. The first design programs came about in 1970. As it happens, at this particular conference, we will have a get together of all what is called the legends of fracturing. So it's all the people are there, and it's quite nice actually to see them around still. It all evolved during the 1980s, 90s roughly, to a state where we are actually using highly sophisticated computer modeling. There's a whole bunch of them around. The list I have there, MFrac, FracPro, etc., they're probably not complete. There's more around. And we do nowadays, we use these models to do on-site job control. In other words, you run the model real time with the information you get from the well during the treatment to make sure that, and modify if necessary the treatment to make sure that it is the best thing you can do. Going back to a little bit to the basis of all this, hydraulic fracturing is all about increasing productivity of the well. basically by, there's two important parameters, a so-called fracture, a dimensionless fracture conductivity, FCD, and a dimensionless length, LCD. And the whole trick of hydraulic fracking is make sure that your FCD is more than 10. Let's forget about the details of this thing. And it's shown here in this, one of the legends of fracturing people, Mr. Pratt, a steady state solution, where he shows that if you have about 10 and a length of something like half the drainage radius, basically that's what LCD is, you can expect something in the range of a 5 times increase in productivity, which is obviously tremendous. Now, it's very difficult to get over here, because this already means sometimes you have a very long fracture. It requires a very big operation, 1 million pounds of proppants in that sort of range. But it can be done. Nowadays, the modeling we use for that includes reservoir modeling. We can look at different configurations, like one vertical well with one fracture, or with one horizontal well with maybe 5 or even more fractures. I think the record on this is something like 15 fractures in one well, but I'm not really sure about these numbers. And the reservoir engineers will probably shoot at me now, but for all simplicity, you could argue that to get to these higher levels in FCD, you need a longer fracture. To create that longer fracture, you can argue, can almost like suppose that the fracture half length is increased quite a lot if you make, in this case I've drawn here 5, but you can think of 4 or 6 or whatever number of fractures. You can actually get quite easy to that high level. So by doing that, you increase the fracture productivity by another factor 2 or so. So you can almost go up to 9 or 10-fold improvement compared to a non-fractured vertical well. So it's quite an achievement you have there. The other option, it's not an option. The other difficulty with creating multiple fractions in horizontal wells is that it is a very costly operation. It can sometimes take up to a month to actually do this, with rig time and all involved. So it's a very costly operation. So people have been looking for simpler ways of getting this done. And one of the ways we have explored is to create a horizontal well and create more than one frac in one go. Instead of actually completing the well with a casing and perforations, we have, in this case, we used a pre-drilled perforated liner with some certain sections we perforated additionally. In this case, we made 2 sets of perforations here and here. And this particular incident, actually the well itself was a bit of a no-hoper, because what happened in this well was that they tried to put a liner in. The liner got stuck 180 meters from the toe of the well, and then after a while they thought, well, let's try and produce. It didn't produce because they couldn't clean out the well properly, and obviously they, as a last resort almost, say, can we actually frack the well? Well, we said, well, it might be difficult, but of course you can. So we actually did that, and you can see here that the productivity of this well, and forgive me about the units they use, it's the German way of expressing the rates of gas well, 6,000 cubic meters per hour to about 61,000 cubic meters per hour, so a factor of roughly 10 improvement. We think we actually have, based on production logging results, that we have created 2 fracs. This one in the middle probably slightly bigger than this one. And there are indications that we even have a 3rd frac at the toe of the well, which we didn't expect. But apparently there was an initiation point for a fracture as well. So this is a technique that can be used quite successfully, and it's a lot cheaper. This took 1 day. The other ones 1 month. You can imagine cost difference. Before we switch to another topic, I really want to make a point here is that if you believe in all those modeling, so let's reflect back a little, if we believe in all those modeling and really follow it almost to the letter and do all this real-time stuff, you have to be careful because these are pictures of mind-back fractures. I believe it was in Colorado, but I'm not 100% sure. And you can see here that the fracture came this way, didn't really know where to go at this point. There seems to be a bit of a barrier here, and it went two ways before joining up again. There's no model that predicts this. So if this happens and you are happily going on with your real-time modeling, you may be in for a surprise. And this one is even more of a surprise, although some people believe that it can be modeled. Here you see that the fracture continues up to this point and then stops, apparently, and starts somewhere else. Now, this is a 2D picture, so you can imagine in 3D picture that at that point, this fracture here made a peculiar turn. And some people have developed models to actually predict that sort of stuff. And it's called, some people call it tortuosity. Other people talk about obstructions in the fracture. But basically, these things are recognized and sometimes are put into models as well. Anyway, before we continue with the new challenge, I'm still working on the old business. Since the beginning of hydraulic fracturing treatment, we had a whole lot of activities. In practice, we believe that probably every single well will see will see a stimulation treatment in the course of its life. We're talking about acceleration of oil production, or gas for that matter. Sometimes, especially in hydraulic fracturing, we're also talking about an increase in economic reserves. And if we look at the benefits over the last 50 years, very difficult to establish, to look back that far. There are really no really reliable statistics about it. But we believe that we have in Shell probably produced about 1.8 billion of barrels, oil equivalent over those 50 years, just due to stimulation. And the cost of that is roughly about 10% of the cost of drilling new wells. So the same amount of oil you can produce by drilling a new well, that is 10 times as expensive. We look at how you design treatments, no matter what kind of treatment it is. There's a phase where you start looking at candidates. You start looking at the kind of treatment you want to do. That's the first phase of the whole workflow. Once you've decided what sort of treatment you want to do, it's about fluid selection, about proppant selection, other materials, how to place it. Eventually you get a pumping schedule, and then you try to simulate first what happens with that pumping schedule. You're still in the simulation mode. And then you have the execution of the job, sometimes just by post-job analysis, sometimes real-time activity. And I'd like you to keep in mind this process. This is a process we talk about. 3 elements: candidate selection, treatment selection, then the treatment design, followed by the execution and the evaluation of what's going on. Switch back to a completely different topic. About 150 years, 160 years ago, a guy called Colonel Drake drilled a hole in the ground. And he didn't have a clue what to do with it, other than use it as medicine. But it's supposed to be the first well. Not everybody agrees with that, but when I gave this talk in Russia, I can't find my mouse back. When I gave this talk in Russia, they said, no, not the Americanos, we did it. But okay, let's assume that this is still true. And it changed quite a lot. And I would like you to look at this picture in the sort of changes we have come over in the last 100 years. And this actually this change took 4,000 years or so. This is, the first is a little stone everybody had in his pocket, and nowadays it's a pair of car keys. So that change, that sort of dramatic change, occurred in the oil industry in the course of, let's say, about 100 years. We've got now multilateral, smart, horizontal wells, and wouldn't it be nice if we could add a few hydraulic fracks, for instance, in those separate legs, except that we don't know how to do that. There are a few things that you can try, but it's not really proven technology that we can do that. So if we look at the new well configurations since the 1980s, we have horizontal wells, we have multilateral wells. In Oman, we have a couple of fields where we literally drilled like fishbone wells, 7 or 8 side tracks on one main track, sometimes 2 above each other, so that you actually have, for water flooding, for instance, you have a direct pattern from the water upwards to the producer. We have smart wells. People put all sorts of nice gadgets in wells to make them smart, really. Subsea completions, Arctic completions, whatever. There may be a whole lot more of things. And very often we find that the conventional stimulation methods that we have, them hydraulic fracturing and acidizing treatments, are no longer applicable, really. Sometimes you still do it because, okay, there's nothing else we have, but it's not really sufficient. So we were given the task in about 5 or 6 years ago, maybe even longer, to look at the possibility of new technologies. We looked at the technologies that were sometimes not all that new. Acoustic methods. Maybe if you shout to the well, maybe it starts producing better. In fact, if you look at it, Moses was probably the first one that did that. He hit the rock, and all of a sudden, that's probably an acoustic effect. Application of heat. And there may be more. We looked at the removal of mudcakes, for instance, by acoustics. And I'd like you to have a look at this. What you see here is a piece of core material with where we artificially put a mudcake on top of it. And then we hang just above it, above the surface, we hang a acoustic horn. And in the picture you can actually see that it will be removed entirely. If you look at this part of the picture, you can see the guy is putting a little paperclip on top of it, and it's completely neat. And in fact, he tries scraping off as well to compare what the drillers used to do. Is scraping the mudcake off. You can see with scraping you only have the surface of the mudcake removed, but not this small internal part of it. And you can see here that it's completely clean. So the frequency range we are looking at is somewhere between 5 and 40 kilohertz. There's a couple of mechanisms that are working here. The particles are detached due to an effect which is called the microstreaming. That's probably not all that important. The main thing really we're looking at is destruction of the bridges you create here. This is actually causing a reduction of natural flow. And you can imagine that if you can break that thing up, you will have a far better production. The other thing we're looking at is viscosity decrease due to the heating. If you apply acoustic energy, all that acoustic energy is absorbed and transferred into heat. It can easily be around 50 to 60 degrees hotter after 2 or 3 minutes of acoustic energy. And then there's an effect which not really works under pressure so well. That's cavitation. That works in low pressure wells. It still does work, but if you go deeper, in deeper wells, it doesn't really work anymore. For this particular technology, we're aiming at removal of damage near wellbore, things like mudcake remnants, or you can see later on as well an example where we look at screen cleaning, sand screen cleaning. There's the important thing is the area of influence. You can have a very low frequency that go very far into the formation. In fact, surface vibrators are used, basically the seismic trucks stamping on the ground and you get oil. It does work to some extent, but the well shouldn't be too deep, obviously. Downhole, you can use these things downhole. There's a technique called pressure pulsing. All has been tried and it all works to an extent, but not really very good. Acoustic cleaning, and something I will talk about a little later, pulsed power, will probably do that. But the disadvantage of that is, of course, that usually it's higher frequency, and because of that, it doesn't penetrate that far. So it's really for mudcake removal, for near wellbore damage. This is the equipment the tool we created based on that, together with a service company. And now, if you listen carefully, you will hear a very high-pitched tone. That is exactly the sort of tone we use. We're cheating a little bit here because the actual frequency we are using is about 18,000 hertz. If we would show that, nobody would hear anything except the dogs would walk out of the room. So if somebody walks out of the room now, so the first tool we have was successfully tried in January of 2005. We repeated some, it says here current, but those are done already. We repeated some trials in the Middle East, and we actually have around 30% increase in productivity, usually with pretty short pulses of acoustic energy. And the important thing is that you have to have some flow during this kind of stimulation. So you don't shut in a well, which is a big advantage because it reduces the deferment of oil and gas tremendously. People like that very much. Even if it doesn't work as well as an acid treatment, for instance, they still would like to do this sort of thing because it saves an enormous amount of money in doing it. And besides, it's not involving any pumping, it's just a kind of wireline operation. So you can afford to repeat it more often than an acid treatment. Every 3 months is no big deal, really. We're now working on a slimmer tool. The first prototype tool was pretty big and couldn't fit in many wells. We're now working on a slimmer tool that would fit in maybe 90% of all the wells. This is the first treatment, which was actually done in a water injector. And it's not the best well to treat it on, but of course people don't like you to use novel technology for the first time on a good producer. This is a water injector in California. And you can see, if you look at this, if we concentrate on the injectivity graph, you can see that the injectivity increased from about 0.06 to a little over 0.012. So roughly a doubling of injectivity of in this particular instance. Unfortunately, they put on the injection of the dirty water again, and a day later the effect was gone. Basically because everything was plugged again with the new material that came in. We're not the only ones. There's other people that work on the same thing. And basically they come to the same conclusion. You need flow during the treatment. And in fact, this particular tool was tried. It seemed that the best production is at high rate. The best improvement is actually at high rate wells. So it's a bit rate dependent how well the well responds to it. So this is a tool which does exist at the moment. We're working on it. It's getting close to actually field application, more widespread field application. Now I'm going to the future. This is a tool we're developing again with another service company, and it's basically using electric sparks to generate shock waves, and the shock wave will again pulverize whatever damage is there. This is basically electric sparks. It shows how it works. Now what we did in this particular test is we put the electrode inside the a piece of sand screen. We actually damaged the sand screen completely with plaster of Paris, actually 2 centimeters thick, so it was completely plugged up. And we pulsed for about like this for about 5 minutes. And then we took out the screen again. There was flow. You can see here we have flow all the time. And you can see that the top part of the screen is completely clean. All the plaster has gone. This took only 5 minutes. The top part, that's where the electrode was. So it's very zone specific. You have to treat this. You use this tool as a logging tool, going very low, slow pace, going up or down. You can see most of the damage was actually gone. This would, in the real world, this would mean that the well is flowing again. This shows, without this gravel pack around it, shows how it comes off. It's not a real world, but you can see it just falls off in big pieces in this case. If there's gravel around it, it is all pulverized and is flowed out. It becomes very fine particles. It's also possible to clean tubulars, for instance. So this is the only part that is not just really what I defined as well stimulation, but you can see that before or after the treatment, the scale, in this particular case, scale was completely gone as well. It's very powerful. And in fact, it's so powerful that you have to be a bit careful how to use it. We actually got this idea, this technology, through the Strathclyde University in Glasgow, who actually developed part of the technology for the demolition industry to demolish buildings. You can actually make it quite dramatic. Also, the military uses the same sort of technology to destroy things. So we're not really, we have to be careful because we don't want to destroy anything here. So the trick is to have a very precise amount of energy put in. Just a few pictures on electrical heaters. That's another way of stimulating a well without actually pumping anything. You just have heaters, electrical heaters in the well. It's a known technology which has been around for a while as well. So the question now is, we have car keys. And what will be the next thing we have in our pocket? Over maybe not 4,000 years from now, but maybe only 50 years from now. Who knows? So to actually get there, we need to think out of the box and get some new technologies developed. I was just showing a few starts here, but there's more to come. So I'm now really in the future, really like being in a dream. Get this picture again. What if we could put this whole process in an automatic mode? In other words, we don't have to decide when and where to stimulate a well. The well does it on its own. We have a self-maintaining well. For that, we need a few new things. First of all, we need to know where the damage is and what the damage is. So we need to know really, find out a kind of logging tool for impairment. I don't know whether you noticed that in the meantime the picture has changed a little bit. This is the Middle East solution to a new logging tool. This is not exactly what we wanted, but it gives you an idea that you may actually be thinking out of the box. So we need some impairment logging tools. We need a lab on a stick. We need, well, this last picture doesn't really belong to it here, but we need a new logging tool. Now, if you use Google to find new ideas, you get a bit strange logging tool again. It's not really what you want. But never mind. This is a technique which already is existing as well. It's used in the medical industry. It's basically almost like a small chip that you swallow, and the doctors, by following what signals come out of the thing that swallowed during the path it takes through your body, can find out something about diseases you may or may not have. It's basically chemistry on a chip, which I think if we use that idea, we can actually put that downhole as well. So I'm already coming to almost to the end of my story. If we start off with an optimum well, so the well is completed in an optimum manner with good impairment control during drilling, with well equipped with monitors, a lab on a stick, maybe logging tools, or almost like stationary logging tools. And we haven't got a clue what that should be. It's future, we don't know. We need new ideas. If we had downhole software to analyze whatever the monitoring part tells us, and to decide whether we want to stimulate using a heat coil, or maybe using what we've nicknamed it a waves tool, whether it's a pulse power or an acoustic tool, or maybe even another tool that's been developed. And if we would have downhole power, that's another important thing. Of course we need power for all this, but of course we also have power downhole. The well is flowing, there's oil, there's gas, there is energy already available. So, and in fact, there is a couple of people working on downhole fuel cells, so you may actually have them. If you have all that, you have your self-stimulating well. You can imagine that you monitor, analyze, we don't do that, the well does it, stimulates, and continue. And you go through this cycle for how long it takes to abandon the well. And there are ideas even about self-abandoning wells. If you put chemicals in the well that create, they're called termite chemicals, if they create temperatures up to 5,000 to 6,000 degrees C, the whole thing will melt down. Thank you very much for your attention.